Hello everyone, my name is Zeren Sun and the paper I'm presenting today is PNP Robust Learning from Noisy Labels by Probabilistic Noise Prediction. So let's get started. So here is a little bit background of this work. Due to the strong capacity of deep neural networks in memorizing and overfitting all data, including noisily labeled ones, DNNs are prone to obtain inferior performance when training with noisy labels. In the past few years, many works have been proposed to address this issue. It has been demonstrated that DNNs tend to fit clean samples in early stage and gradually fit noisy ones as the training proceeds. Samples with lower losses are more likely to be cleanly labeled ones. This leads to a promising sample selection strategy, which regards small loss samples as clean ones and discards high loss samples directly. Recently, some researchers proposed to distinguish in-distribution noisy samples and out-of-distribution noisy samples. They accordingly proposed to identify clean, ID noisy, and OD noisy samples and treat them differently. Early sample selection methods tend to deem samples as either clean ones or noisy ones based on the low-loss criteria. Once noisy samples are identified, they are discarded from the training process. Despite promising results have been achieved from this strategy, these methods neglect the differences between in-distribution noisy samples and out-of-distribution noisy ones. High-loss samples are not necessarily wrongly labeled ones and are also potentially beneficial for model training. Recently, researchers start to treat in-distribution noisy samples and out-of-distribution ones differently. However, the process of identifying clean, ID noisy, and OD noisy samples tends to introduce hard-to-tune and dataset-dependent thresholds. Ideally, we hope to have a model which can predict the noise type of each sample in a probabilistic manner. Consequently, the final objective loss can be a weighted average based on the predicted noise types. So, we propose an end-to-end framework to achieve this goal. This is the workflow of our method. Our method mainly consists of two networks and three losses. Firstly, we simultaneously train a label predictor network and a noise predictor network. The label predictor network aims to predict the category label, while the noise predictor network predicts the noise type of the input sample. Then, for different types of samples, different classification loss functions are employed based on the noise type. Clean samples use the conventional cross-entropy loss. For ID and OD noisy samples, we treat outputs of strongly and weakly augmented inputs as predictions and targets respectively. Next, to enable the training of the noise predictor network, we adopt an auxiliary constraint loss. When computing this loss, we use JS divergence between prediction label pairs and prediction pairs to approximate the ground truth noise types. Lastly, we impose a consistency loss on in-distribution data to enhance representation learning and strengthen the ability of discriminating ID noise and OD noise. We further evaluate two paradigms of sample selection, hard selection and soft selection, leading to PNP hard and PNP soft, respectively. PNP hard is intuitive and straightforward, assigning each sample a discrete tag that reveals its noise type. On the contrary, PNP soft adopts a reweighting schema when computing losses. While the hard selection can concretely identify the noise type, it may amplify the risk of incorrect predictions, leading to a potential overfitting issue problem. Conversely, PNP soft is beneficial by guaranteeing that at least part of the loss is correctly optimized, even if the noise type is wrongly predicted. Here is the experimental results of our method on synthetic noisy datasets. You can see that our method consistently outperforms the existing sorter methods in both performance and robustness. Here is the experimental results of our method on real-world noisy datasets. We can see that our method is still consistently better. Thank you for your time.